Okay, you ready? Okay. Okay. I think we can start now. So, yeah. So what I'm going to do would be, we will go over the fifth problem fast, to just make sure everybody knows what that question is talking about. Seems that there is a little confusion there. And then there are three questions that I gave them to you. I'm going to post the file later too. It's just that since I posted it, I prepared it 10 minutes ago, I just printed it to give it to you. But the file would be up there too anyway. So we'll try to solve, I don't know, one or two of them at least, Then you can do the third for yourself, whatever. And just some examples on linear programming. And then some people told me that there was some confusion about that oil trading question. So if we have time, we'll go over that. But I think this time should be a very short class, much shorter than previous times. Okay, so first think of let's talk about the fifth question in the homework. And it's not a hard question at all. It's just that I think the wording might be a little bit confusing. That's why you might have had some problem with it. So let's see so forget the numbers there and just let's think what's the idea of arbitrage in that question and what do they mean by finding if there is a arbitrage case, if that's the case of arbitrage or not. So the idea of that question is that you have three types of bonds. Let's call them 1, 2, 3, and each of them at now, right now, let's call it. I'd like to call it time 0. Doesn't matter really, call it whatever you like. At time 0, they have a price. So x1, x2, and let's call them x1, y1, and z1. So let's even forget these 0, 0, 0. It'll just be. So at time 0, each of them have a price of x0, y0, z0 that you can buy. You can buy or sell at this price. And then at time 1, time 2, etc., whatever, each of them have a payoff of x1, y1, z1, x2, y2, z2, and etc. Let's call them x, y, z bonds. Okay, so we have these three bonds, x, y, z, and at time 0, this is their price. And then they pay these things back. So they can be positive, negative, we really don't know what's happening. So let's see what's the idea of arbitrage. The idea is, assume you have no money in your pocket. 0. Okay, you have no money in your pocket. And you come here and see this case, this happening, this whatever is happening here. Now, you can start doing this. You want to buy some of these, obviously. The idea is to buy and sell something to make money. If you can find a case that, let's say, I go to somebody and say, I'm going to sell you one X type bond. So he would pay me this amount. And later, so basically by selling it to him, I'm committing to paying him back this money in future. So I go and sell somebody this bond, and he gives me some money. Now I have some money. I'm going to go buy something for myself. So for the time being, assume this third one is not here at all. So I'm going to buy 1 unit of X, and I'm going to sell 1 unit of X and buy 1 unit of Y. So my money that I would make here would be, I'm selling this one, so I get this money, I have it in my pocket, and I go and buy one of these. So I would have this amount of money in my pocket, and I will have obligation of paying one type of X to somebody in future, and I also have somebody would be paying me Y in future too. So I will make this amount of money at this time. So let's put them numbers. So it was 90 and 100. So I go and sell. Okay, I cannot do this because I have no money in my pocket. So I'm gonna sell one of these and buy this one. So it would give me 100 minus $90, which equals $10. $10 in my pocket, and also 1 Y, and I also have to pay back 1 X. Now in time 1, what happens? So what happens in the next step is, now somebody who you bought this guy from would pay you Y1, and you have to pay this guy X1. So let's put numbers then just arbitrarily, I don't know, 10, 8. So you make $10 and then you pay 8 of it to the other guy, so you end up having $2 at the end. We go to the second step. These can be any numbers, so repaying the whole coupon, expiring, doesn't matter really, just some numbers here. So let's assume that everything finishes here. So 108, so that's really important, let's say 107, and here would be, I don't know, let's say 108, okay? Just arbitrary. Now, this time I'm gonna get this amount of money and pay the other guy back $1. So what happened, I started with no money in my pocket. I went and sold one of these and bought one of these, and without doing anything, without taking any risk, nothing, I ended up having $10 here, $2 here, $1 here. But this is called the case of arbitrage. So in the case that, basically with zero money in your pocket, you made money. Now, in a well-behaving question or something like that, we wouldn't have such a case. This thing wouldn't happen. For example, this would be 108 and 107, and this would be -1. This would be enough to say that there is no case of arbitrage, because depending on the interest rate, this might end up being a good project or a not good project to take. Depends on how it works. Of course, this is a bad number. This is always a good project still. But so unless you can find a case that without having any money in your pocket, with $0, you can. So if you find a case that with having no money in your pocket, $0, you can create a positive cash flow for yourself by buying and selling this stuff, then we can say that it's a case of arbitrage. So now the question is asking you, it has given you a structure like this, which is a little bit more complicated than what I have here, and he's just asking you to see if such thing exists there or not. So let's first start writing down the cash flow that they will generate for us. So there are three type of bonds. So 1, 2, 3, and now October and April, I guess. I'm not sure really. So now the prices are. Can somebody read them for me? I forgot to print them. If anybody has 101.6, 6 to 5,
101.56 to
5, 6 to 5,
103.8.
0.8? Okay. So in October, this would pay me back how much?
6.875 by 2.
6 point. 3.437, and on April it will bring me back 103. Oh no, it was here. This one expired here, yes? Okay, so this was like this, and the second one would give you 2.25. Are you sure?
It's 5.5.
Yeah, you have to divide it by 2. Okay, and this would be 2.75 and 1.02.
The 3.437 is only a coupon.
This one?
Yes.
No, but October it's expired.
It expires to in October, so it's paying you back the real value too. So this plus 100.
Plus, yeah, right.
So plus 100 would be just this. Okay, and the last one would be, what's the value?
7.74.
7.75 would be divided by half. Huh?
3.87.
3.875. Okay. Sorry, I lost my papers. So this is the cash flow that you are facing in this problem. That you can buy these or sell these at these prices, and right now, then this would be the cash flow generated by them on October and on April. Basically, if you buy this one, this would be positives, meaning that somebody will be paying you these numbers. If you sell any of them, it means that this would turn out to be negative. You have to pay somebody these values. Now you have to find a mixture of these guys. Let's call them alpha 1, alpha 2, alpha 3. For example, I don't know, half, 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 meaning that, and let's put a negative here. For example, I'm going to just put negative to see what I mean. So when I put negative here, it means that I'm paying the money, meaning that I'm going to buy that thing. And if I put positive, it means that I'm selling it. So what does this combination mean? Well, let's forget the halves even. It makes it harder. So this combination would mean buy this, sell this, sell this. So you sell this one, and you buy this one. Obviously, at this time, you're going to make positive money. Why? Because you are selling these two, you're just buying this one. These two are greater than this. But when you're selling these two, at this time, you have to pay back these two, and you will get this one, which is possible because this is a lot of money. Somebody's paying you a lot of money. You can pay these to still make positive money. At this period, you're making no money, but you have to pay back these two. So it's a negative thing. So this combination would give you a positive cash flow here, a positive cash flow here, but a negative cash flow here. Now, the question is asking you to find these three numbers in a way that would give you positive in all three cases. Now, first of all, remember you just need to check all the ratios between -1 and +1. Because, if you have, let's say, assume that the answer is this, 10 minus 12 minus 1, meaning that sell 10 of these, buy 12 of these, buy 1 of these. Then just you can rescale it by dividing everything by 23 in this case. And it would be 10 over 23, or even not 23, just divide everything by 12. Then it would be 10 over 12 minus 1 and minus 1 over 12. So this would also give you the same result. Just divide everything by 12. So you just bound your numbers from both sides by anything that you want. And then so look for ratios between -1 or +1 or -2 +2, whatever you like. And then try to find a combination that gives you positive everywhere. So you have to define some objective function, which is not really important at all. It can be any objective function, which its feasible region would be the values of these vectors that make these three cash flows positive at every point. So you really don't care what you're maximizing or minimizing. Who cares? Maybe you want to maximize the amount of money that you are getting from this arbitrage, but the question is not asking for that. The question is just asking, does such case exist or no? So for that, you just make an optimization problem, which is feasible region, or the points that make all these three positive, meaning that I'm going to give you a lot of hints here, but some of these should be positive. These would be your constraints, and your values would be somewhere between -1 +1. And then you put an arbitrary objective function and go ahead to see if you can find it or not. So if that question has a feasible point, that feasible point is somewhere that is giving you these three positive. Remember, there is one feasible point that is not something that you like. It's 0, 0, 0. Just a second. 0, 0, 0 would give you all this stuff. Everything would be, because all your constraints would be greater than equal to 0. So at 0, all of them would do. So try to play with your starting point a little to get somewhere aside from 0, 0, 0. And I think by the way the question is asked, you're sure that you should be able to find something. Then in the second part, he's telling you that buying and selling are at different prices. So you have to, again, do exactly the same thing. Set up an optimization problem, which is feasible region would be the points that make positive value for you. But let's see, but now modeling it is a little bit different. Because you have to make sure that if you are selling, so one way to model it that one of your friends did was to use if-then function in Excel. You say that if this is negative, meaning that you are buying it, use this price. If the value of the vector is positive, use this other price. But that's not linear. We are trying to model everything in linear case. That would give you the correct answer in this case because it's a small question, everything. But if you have a big question, then might not give you a good answer in the sense that you might not be able to solve it. Now, if you remember, I'm going to just tell you the trick how to do it, then try to figure it out yourself. So you can start writing that. Remember, you will have a variable here, which is x, your variable, which can be negative or positive. So if you remember, there was this trick in class that I think Professor Iyengar taught, that any number which is negative and positive, you can write it down as the difference between two numbers. So for example, 10 can be written as 10 minus 0, when x plus and x minus, both of them are greater than or equal to 0. Or if you have minus 10, you can write it down as 0 minus 10. Again, these two are both greater than or equal to 0. So you can change any variable which is, positive or negative. You can take values on positive and negative and write it down as a difference of only two positive variables. Now you know that. So, and you can make sure that one of them always remains 0, the other one remains positive. If you write down your problem and think about it, it's not that hard. So it wouldn't turn out giving you 11 and 1 in this case. Now you can make sure that if you're selling somebody the coefficient of x plus, so if the value is positive, you can put a coefficient here which is the buying price. For this one, you put a coefficient which is the selling price. Now you can start playing with them. So this is the trick that you have to use. Since you can solve it using if-then, I'm not going to solve this right now for you. I want you to think about it a little. You will get the solution anyway. So just start thinking about it this way, see if you can model it or not. This should give you enough hints to be able to do it. Yes?
For number 5, can you assume that you can buy a fractional?
Yeah, you can always buy a fractional. Yeah. But remember, buying a fraction doesn't change anything. Assume that my fractions are this. 0.12, 0.23, 0.11. You can just multiply everything by 1,000, and then you get integer values. So non-integers are not a problem as long as they are just there's no problem. You can always just scale them by a large number, and you can get integer values. Unless you get a number like pi that you cannot scale, but that would never show up for you. So yeah, no problem with assuming something which is not integer. Any other questions?
So if you use if, then we have to redo it?
Sorry?
Like, do we have to redo it?
I would suggest at least think about it. That's not linear. You have remember, some of these questions are easy to model in a non-linear way, but they are not easy to solve when your problem is a large problem.
3 is non-linear too.
Yeah, so that one is a non-linear programming, but this one can be modeled as a linear program. So whenever you can model something as a linear program, you should do it because it's much more efficient. Yes?
You said that we can have any objective function like...
Yeah, any objective function.
Why?
Because you don't care what's the... You would be what the question is asking you is not asking you find the best case of arbitrage. It's asking you find if there is a case of arbitrage or not. Okay? So you can if you want to maximize some of the cash flows. I don't care about it at all what you're maximizing. Because as long as you find a feasible solution for me, meaning that you find a case that all three are positive, you have got the answer to the question. So, but you can maximize or minimize whatever you like. It's not really important. Any other questions?
I don't understand the part. How are you going to prove that you cannot find the...
So again, the idea is the same idea. Set up an optimization problem that its feasible region would be the vector that will give you positive values everywhere. Now, can you talk a little bit less? A little bit, okay. So if you can find a case that, so if that optimization problem has a feasible solution, we don't care if it is optimal or not, just has a feasible solution, then you would have a case of arbitrage. Otherwise, you should have shown that there is no vector that would satisfy those constraints. So your constraints would be making positive money everywhere. That's all.
How does one show there is no arbitrage?
So then when you run Excel, it will tell you this optimization problem doesn't have a solution.
Well, it puts zeros.
So if the only solution, if the only solution is, zero is always a solution. So if it tells you that the only solution is 0, there is no multiple solutions, then you know that there is no other case. That's all. Yes?
So in part B, if solver says it cannot find a feasible solution, that's our...
Yeah, well, 0 would be a feasible solution, okay?
Other than that,
Yeah, other than that, if it's basically, if there is no multiple feasible solution, there is only a unique 0 feasible solution, there is no case of arbitrage. That's it.
I don't think 0, it can be, because the question phrases that the first constraint has to be greater than 0.
Well, you cannot, the thing is, remember, in linear programming, you never have this kind of constraints. And you never have it because we don't know how to solve them.
Okay.
That's the reason. Okay. Nobody knows how to. Well, I'm not saying nobody knows. That's a big claim. But assume that we don't know how to solve them. We don't have an efficient method to solve them. At least that's what I say. So everything is in equality. There should be that equal part. Yeah, this was just, easy, just try to explain what's happening there. Now, let's go to the questions that I gave you. These have more to do with what you did in class yesterday. Now, the first question is talking about, well, the first question is a quote, but the second question is talking about a cargo plane which has some compartments. Now, let's read the question together. A cargo plane has 3 compartments for storing cargo. If you don't have copies, they are here. Some copies here in the front. So a cargo plane has 3 compartments for storing cargo, front, center, back. These compartments have capacity limits on both weight and space, as summarized below. So there is a table which gives you how much the capacity and weight and space, the limit on weight and space for each of these. Furthermore, the weight of the cargo in the respective compartments must be the same proportion of the compartment's weight capacity to maintain balance of airplane. So basically this question is saying that if you are filling 10% of the front compartment, you should also fill in 10% of the center compartment and 10% of the back compartment. You cannot have the case that you fill the whole front compartment 100%, but you just fill 5% of the center compartment. And this is only on weight, not on volume, so that your airplane is balanced, doesn't fall like this. So you have to balance it. Now, the following 4 cargoes have been offered for shipment on an upcoming flight as the space is available. So there are 4 cargoes. We have the weight for each of them. We have the volume for each of them. And we have the profit on transporting on each of them. Any portion of these cargoes can be accepted. So basically this means our problem is not integer. You can take half of it. The objective is to determine how much, if any, of each cargo should be accepted and how to distribute each among the compartments to maximize the total profit. So you should tell, put this amount of this guy in this compartment, put amount of this guy in this compartment, so that your profit is maximized. So let's start formulating it. Any ideas for decision variables? Sorry?
3 weights, 3 compartments.
Okay, so I have an X what? Just tell me to write it down.
X1, the weight in the front compartment.
So X1 would be?
The weight in the front compartment.
Weight in front weight. Okay, so Xi would be weight in ith compartment, yes? So is this what you're suggesting? Well, this might work, but then this wouldn't be enough then. Just a second. Let's So why do you think this, why anybody can tell me this is not enough?
Because you want to distribute the cargo itself into various.
Yeah. So this would tell you, if you define your variable this way, it would tell you put 10 tons in the first compartment. But it wouldn't tell you this 10 ton comes from which one. So maybe so your decision variable should be in a way that tells you put 5 kilograms of this cargo in this compartment. So how do you suggest to change this?
Xij.
Okay, Xij. So Xij would be weight in ith compartment of jth cargo. Okay, good. Let me just make sure that it's the same notation that I have myself. Otherwise, I have to change this a little. Let me just see. Okay, yes, I have the different one when I was solving it. So weight in the jth compartment from the ith cargo. I don't want to rewrite all my solution. So this would tell us how much of the jth ith cargo to put in the jth compartment. Now let's start. Okay, in this case, I think it's easier to write down the constraints first. So let's start writing down the constraints. The first constraint would be the weight constraint that we are working for each compartment. So we have the front compartment. Let's call it the first compartment. Then we have center compartment and the back one. Okay? So these are the compartments. Now we are writing the weight the constraints on these guys. The first one is, well, let's forget this one. Okay. So the weight constraint would be, so what would be the weight of
xi1.
xi1.
Summation.
Yeah, just a second. I'm making a mistake here, I think. In my... Okay, no, that's right. So, x front compart x11 plus x1, so x21 plus x31 plus x41 should be less than equal to the capacity of the front compartment, which is 12 tons. Okay, so this is my first constraint. It's telling me that so it's telling me that the amount that I put in the first compartment from the first cargo, second cargo, third cargo, and fourth cargo, when I add them up together, should be less than 12 tons. So then we would have the same constraint repeated for the other two compartments, just a little bit different. It would be 1, 2, 2, 2, 3, 2, and 4, 2. This should be less than equal to, somebody tell me the number? 18. Good. And then the last one. This should be less than equal to 10. So this is taking care of the weight constraint for us. Yes?
Don't they need coefficients though?
No, they don't need, because I'm just saying this is the weight itself.
Oh, okay.
Okay, this is, yes.
There will also be some more in order to incorporate the weight of the orders themselves, as in, for example, you have the weights 20 tons, 16, 25, 30 for the other table as well. So you'd sum them up too, in order to come up with more constraints?
No.
No, sorry, I didn't get your question.
Because the weight is also constrained for each type of cargo. You have
Yes. Yeah. That would be a different constraint. We are not, this is the compartment constraint, and only on weight, not on volume. So we are just making sure that you are not putting more in any compartment that you are allowed to, weight-wise, not even volume-wise. Now, the second weight constraint is what you told me, that you cannot put more than what you have demand. So let's put it like this. So for the first, so let's put it like cargo type. Cargo type 1, 2, 3, 4. Now, how much of cargo type 1 I'm putting in my airplane is these guys? I'm putting some of it in the first compartment, in the second compartment, and the third compartment. So the amount of cargo 1 that I'm putting on my airplane totally should be less than the amount of cargo 1 that they are offering me. I cannot, put something which doesn't exist in my airplane. So this should be less than 20 tons. So it's basically saying that amount of cargo 1 which I'm carrying is less than the amount that I'm being offered. Again, exactly the same constraint exists for cargo 2, cargo 3, and cargo 4. Uh, 16, 25, and 30. So this is making sure that you are not carrying something that doesn't exist, basically. You would carry something that exists. Now, the next set of constraints that I will have, okay, I'm just taking care of the weight constraints first, then I would go to volume constraints. You have that weird second paragraph that says, furthermore, the weight of the cargo in respective compartments must be the same proportion of the compartment's weight capacity to maintain the balance of airplane. So we have a balance constraint. So how do you propose to model this one?
X11.
You go ahead. X11 plus X21 plus X31 plus, okay? Divided by 12 is the capacity, okay? Exactly, you're right. 18. Well, I cannot write as fast as you talk, so give me a second. x23 plus x33 plus x3, 43 divided by 10. Okay, so let's see what this constraint is saying. So this is saying this is the amount that you put in the first compartment, the front one. Divided by the capacity of the first compartment would be the ratio that you're using. So you would be using 10%, whatever. So it's saying this ratio should be equal to the ratio of the capacity on the second compartment that you're using, should be equal to the ratio of the capacity on the third compartment that you're using. So basically this makes sure that your airplane stays horizontal, doesn't fall off. So this would be the balance constraint that you have, the second paragraph constraint. Now the last constraint which is left is the volume constraint. Well, there is one more constraint left aside from that one too. We'll go over it. Now let's think of the volume constraint. So if you check, we have the volume in a sense of cubic feet over tons. Basically you have some density type volume. So you can just use that multiplied by the weight and see how much volume you have. Otherwise, if the volumes were given to you just volume-wise, then you had to define a new set of variables exactly like this. Let's call them Yij, which were the volume of the cargo. And then you had to link Yi and Xij in a way to each other, which would have been a harder problem. So we are not worried with that yet. So but here we have it in a good way. We have the cargo one, its volume is 500 cubic feet per ton, for example. So if we want to make sure that in the first compartment we are not putting more than what it fits, volume-wise, we will have X1 is the amount of cargo 1, X11, amount of cargo 1 that we put in the first compartment. Multiply it by 500. This would give you the volume of the first cargo that you are putting in the first compartment. Adding this to the volume of the second cargo that you are putting in the first compartment. And then the third cargo that you're putting in the first compartment, and then finally the fourth cargo. This should be less than equal to the volume of the space capacity of the first compartment, which is 7,000 cubic feet. I have no idea how much is a cubic feet. So this would be the amount that you can put in the first compartment, which shouldn't exceed its volume. Now you write exactly the same constraint for the other two. You write them yourself. I'm not going to write them. So you have to write the volume constraint for the front, for the center and back constraints. So this will also take care of the volume thing. So are all the constraints written or no? Okay. So let's see what it was. So where did I read this 500? I read it from the second table, which says the volume of the first cargo is 500 cubic feet over ton. So if I'm putting this amount by ton in the first compartment, if I multiply it by 500, this would be the volume of it. So this is the volume of the first cargo that I'm putting in the first compartment. Plus should be less than capacity of it. Now, any other constraints? Yes, that's very important. So never, you will forget this one a lot. So never forget it. All your variables are non-negative. If you don't put that, your model is wrong. That's it. It's wrong. Okay? So never forget this one. This is very important. Now, the last thing which is left is the objective function. So anybody can tell me the objective function?
320 into x11.
Sorry, 3?
20 into bracket open.
Okay, I write it as sigma.
x11.
x1, x,
1j.
1j. J is from
1, 2,
3 plus
400.
400 sigma x 2j. J from 1 to 3 plus how much?
360.
360 sigma x 3j. J from 1 to 3
290.
290 sigma x 4j. J from 1 to 3. And maximize or minimize? Maximize. So you're maximizing the profit that you're getting. This is the amount of cargo 1 that you're carrying it. You don't care where it is. This is its profit. Amount of cargo 2 that you're carrying, multiplied by its profit. So you would be maximizing the profit that you're making on this trip, and you're satisfying all the constraints that you have. Then if you like to make your question more realistic, try to put other constraints, try to model them. Try to think of that you cannot put this cargo and that cargo in the same compartment, how to model it. Sometimes it's not easy to think of them. You might need to think of some, auxiliary variables to help you. Just, something to give you to think about. Now, let's go to the third question first. Because I like that question more than the second one. Can I erase this? Okay. Okay. In a manufacturing plant, the final product is the result of assembling 4 units of A and 3 units of B. So 4A plus 3B give you 1 unit of final product. You can think of them as, some work in progress, some semi-finished goods that you put them together, assemble the final product. A and B are produced by mixing 2 different types of raw materials. Okay, if there are typos, grammatical error, I just typed them in 2 minutes. So there are 2 types of raw material, RM1 and RM2. We have 100 units of RM1 and 200 units of RM2. So we have 100 units. Okay, when I'm writing down, summarizing my problem, I'm just writing the way I like. You would develop the way you like to summarize the data, so that, don't copy it. Just write down the way you feel comfortable. So I have 100 units of RM1 and 200 units of raw material number 2. Now, mixing of raw material number 1 and RM2 can be done in any of the 3 departments of the plant. So there are 3 departments in the plant. Each of the departments uses a different manufacturing process. The following table shows how these processes consume RM1 and RM2 to produce A and B. So you have 3 departments. Let's call this one Department 1. So in Department 1, you have to use 8 units of RM1 and 6 units of RM2 to produce 7 units of A and 5 units of B. Okay? In Department 2, you use 5 units of RM1 and 9 units of RM2 to get 6 units of A and 9 units of B. And finally, in the, well, not everybody sees that one. In the third department, we use 3 units of RM1 and 8 units of RM2 to get 8 units of A and 4 units of B. Okay? So these are how the different departments work. Now, so for example, in Department 1, each production cycle, okay, so these correspond to 1 production cycle. So in each cycle, you consume this and this, and you get this. In each production cycle, we have to use 8 units of RM1 and 6 units of RM2 to produce 7 units of A and 5 units of B. Find the number of cycles each department has to work so that we can produce the maximum amount of final product. Okay, so now we just, we know how much of these we have. We know that they produce A and B in this fashion, and then A and B are assembled themselves together to make the 1 unit of the final product. Now the question is to tell each of these departments how much to work, basically how many cycles to work, so that our profit is maximized. Any ideas for the decision variables? Yeah, that's really easy. But then we would see that it's a nice problem in the sense that some parts of it, modeling it might not be that easy. Okay, let's erase this one. So the best, the obvious choice seems to be the number of. Well, this one is not that tricky, but did you solve that nurse scheduling problem in class too? And I think did Professor talk about that the first variable that comes into my mind is not the easiest one? Well, this one I think is, but I'm not sure. Let's see. So we define xi to be the number of cycles that department I should work. Okay. So xi is the number. So for example, x2 is the number of cycles that department 2 should work. Now, interesting. Okay. I brought my wrong pages, so I have to model it again. Let's hope that I can remember how I did it. Now, let's see. So first let's start on the constraints. They're easier than the objective function in this case. So what would be my constraints? What are my constraints?
Raw material.
Sorry?
Raw material.
Raw material. So basically my constraints are on raw material. Okay, so I should make sure that I don't use don't use this. So for raw material number 1, I don't go above 100 units that I have. So how much, if these are my decision variables, how much of raw material 1 I'm using? Exactly. 8x1. So whatever number of cycles x1 is, the first department would be working, I would have to use 8 of units of raw material 1 plus 5x2 plus 3x3. This should be less than or equal to 100. So this would make sure that I don't use some raw material that I don't have. I would just use at most 100 units. Exactly the same thing goes for raw material number 2, which would be 6x1 plus 9x2 plus 8x3 should be less than or equal to 200. Okay? So this would make sure that raw material number 2 is also okay. Now, any other constraint? Yes or no? Yes, xi's are non-negative. This is important. How many? Yeah, I just put it here so that you don't forget. Any other constraint? Nothing? Okay, that's a good question. Yes.
Xi should be integers.
Okay, forget integrality. We are not working with integers here. Everything can be partial. You can make half of this. That's fine. Okay. Now that's a good question. That where does this come? We are not maximizing A or B. We are going to maximize the number of the final products that I'm using. So, and we would see that it would show itself in the objective function. So let's see how you would formulate the objective function. Any idea? What's our objective? What are we maximizing here? So we are maximizing what?
It's 4a plus 3b where a is equal to 7x1 plus 6.
Let's write it down.
It's actually
Okay, one by one. Let's go on. So you go ahead.
4a plus 3b.
4a
plus 3b.
plus 3b.
Where a is 7x1.
Okay, so let's just tell me to write it here.
7x1 plus 6x2 plus 8x3
Plus 6x2
plus 8x3
8x3
plus 3a2 5x1
5x1
9x2 and 4x3
9x2
and 4x3.
4x3. So I will be maximizing this. Let me just see. I really don't. This is not what I have in my mind. Let me just check this. Just a second. Let me see if this works. I don't think this would work. I will tell you. Divided by 4. Okay, just one by one. One by one. Okay. This thing wouldn't work. Let's see why. Let's just see why. You know, I don't want to just say no. Think of this. Assume that x2 is 0, x3 is 0, 0, 0. Okay. And you put x1 to some number from here. Okay. So 0, 0 and x1, 10. This is the feasible point. 10, 0, 0. Okay. Now 10, 0, 0 will set your objective function to what? 50, 150, 70, 280. It would be a positive. Let's say it's 300. I don't know, some number. So basically, but 10, 0, 0, what does it mean? It means, I see your point. Let me see. Maybe this works. Maybe I'm wrong. No, this is wrong. Yeah, because this is not giving you the number of units that you can produce. This is giving you something that I really don't know what it is. This is not the number of this is not the number of units that you're producing. This is just something. Before you, there was something else. Yes? Sorry?
They should be divided by 4.
Okay. Okay. Divide them. So divide them by... We are moving in the correct direction, but this is still not the correct one. Huh? You have to add constraints? Okay, if you can add constraints and correct it, that would be fine. Okay, think of it. Don't tell that. That's my answer. Okay. Okay, it seems that everybody is on the correct path. So let's... Okay, maybe you can do it by adding constraints. I'm not sure. Okay, well, these have normally infinite number of ways to be modeled. So, yes.
Can't you just say 4a has to equal 3b and then solve the maximum with that?
4a.
Has to equal 3b.
Okay. Oh, this is a good question. Let's just wait for a second. Listen to this, please. This is a good question. Can we impose in a way, please? Okay. 4a equals to b. It's not necessarily correct because you might end up telling these guys to run in a way that you have to discard one of these a little, but then you can produce more. You know what I mean? Because it's a good idea, but it wouldn't work. You don't want it to not have, well, that would make sure that you have no waste. So if your objective function was to minimize the waste, that was good. Because that would make sure that whatever you produce, then you can just make enough final product. But we are not worried about that. We just want to maximize our profit. Maybe we have to discard some A or some B. Obviously, we won't have to discard both of them because there's a proportion. One of them would be more than needed. But that was a good question. Now, there was this idea. Well, it's easier to write it down than explaining where it comes from. Maximize minimum of 7x1 plus, we have this here, 6x2 plus 8x3 divided by 4 and 5x1 plus 9x2 plus 4x3 divided by 3. Okay, let's see what this means first. Okay, assume that we have given the numbers to them, some numbers, and we have produced some amount. We have ended up with 10 units of A and 20 units of B. Okay, 10 is not good. I want a number to be divisible by 4. So 16 and 21. Okay. Now, so I have ended up with 16 units of A and 20 units of B. How many units of final product I can produce? This is just a simple question. 4. Where did you get the 4 from? 16. Okay. So you say that you divide 16 by 4. It gives you 4. Let's make it 12. I don't want to get the same numbers. 12, 12, 3. Okay. So I have enough amount of A to produce 3 units of final product. How did I get it? I just divided it by the amount of A needed in each unit of that. Now, if I have B 21 units. I need 3 units of B to produce 1 unit of final product. So this would give me 7. So I have enough B to produce 7 units of the final product. I have enough A to produce 3 units of the final product. So basically I can produce only 3 units of the final product. Is this clear? This is very crucial here. This is the main idea here. Again? Okay, why not? So let's see. The question was, forget everything. This is a very simple question. You have 12 units of A and 21 units of B. How many units of final product you can have? That's a very simple question. When they mix in this fashion, that 4 units of this and 3 units will give you 1 unit of the product. So let me just explain this. So we have 12 units of A ready. We know that we need 4 units of A to produce 1 unit of the final product. So you divide it by 4. You have enough A to produce 3 units of final product. The same fashion for B. You have 7 units. You have enough B to produce 7 units of the final product. So you start mixing them. You make the first 3, then you run out of A. You have some extra B, which would be leftover waste, whatever. So how did I get it? I just divided the amount of A by 4, divided the amount of B by 3, and took the minimum. Okay, now, what's the question?
The thing is the 4A equals 3B thing, though, wouldn't that kind of do the same thing?
I'm not sure.
If you say that they're equal, and you say you maximize either 3A or maximize 3B, it's already going to take the minimum of those two, because it's constrained that they have to be equal, right?
I'm just saying in the optimal solution, they might not be equal.
Well, yeah, but if you maximize either 3A or, like, so your objective function doesn't matter. If you set the constraints equal, then you're saying that you're going to either maximize 3A or 4B.
Yeah, but
it's going to have the minimum condition built into it.
I don't think that would work because when you I don't think that would work. I can explain it for you after the class, but I think that wouldn't work. So now let's see. So does everybody get where this comes from? Because this is exactly the same thing. So this is giving you the amount of A you produce. This is giving you the amount of B that you produce. And just the same logic applies here. I get this. So is this clear or not? Yes or no? Yes or no? Okay. Now, what's wrong with it? It's not linear. Okay. The basic problem that we always have. This is not linear. Now, somebody who hasn't seen this before, has any idea how to make it linear? Now, those who have seen it before, any idea how to make it linear?
What you could do is that you could solve them separately. Make it take your objective function as then whichever is the lesser one.
Okay, solve them separately and pick the smaller one. I think that should work, but that's not what I'm looking for. Now, think of adding some variable to the problem. This is the hint. Those who were, in their undergrad were industrial engineer, they should know this. This is a very common trick. Think of adding a new variable to this problem. Let's call it y. And y equals this minimum. So if y equals minimum of A and B, what's the characteristic of y? So what's the relation between y and A? Is y greater or smaller than A? Okay, y is less than equal to A. What about B? Okay, less than equal to B. Y is less than equal to B. Now, let's think of the trick here. I'm saying to say, forget this. My objective function would be maximize y. While y is less than equal to 4x1 plus 6x2 plus 8x3 divided by 4, and y is less than equal to 5x1 plus 9x2 plus 4x3 divided by 3. Okay, so now what it's going to do, it's going to try to maximize y as much as possible, and it would hit one of these two first. So basically it would be maximizing the minimum of these two. This is a very, is it clear or no? This is very important. So now, remember, these two by themselves, without the maximization function, wouldn't guarantee that y is the minimum. Because I'm trying to maximum the y would turn out to be the minimum of these two guys. If I was maximizing some other function, if I was minimizing some function, then this wouldn't work, this trick. Why? Because this is just making sure that y would go as high as possible because my function is maximizing. So all these machinery together ensure that y would be equal to minimum of these two functions. That's a very common trick that you would see a lot of times. Well, obviously you can have maximize minimum of a function too. So here we are maximizing minimum. Then you can minimize maximum of two values too with the same trick. It doesn't need to be only two variables. It doesn't need to be. Okay, so if we had a c coming from here, the same trick would have applied. You know. So this is some nice idea. That's all. Any questions about it? Now, just a second. I think your idea might work, but you have to find good constraints to put there to make sure that it works. I really don't know how to do it. Just think about it. Yeah.
Could you repeat the trick, please?
Okay. Well, it wasn't something really fancy. I used this fact that so I said if y equals minimum of a and b, then y is less than equal than a and y is less than equal to b. Okay. And the maximum value of y would be equal to minimum of a and b. Okay? Because how much can it go up? It can go up until it hits one of these two. Whichever one it hits first, it would be equal to that one which is the minimum of a and b. So I say, instead of, after writing down my constraints, I would say maximize y when y is less than equal to this and y is less than equal to this. What were these two values? These two values were the amount of a, this amount, so this would give you the amount of a that you have to be able to produce the final product, and the amount of final product that you can use having units of b. So, obvious, well, in a normal case, one of these two constraints would be tight, equal, the other one would be inequality, meaning that you will end up wasting one of those two. You might get lucky and then both of them would be satisfied at equality, then you are not even wasting anything. So since in our case, so now let's make an observation. Assume that we also want to have a constraint on our amount of waste. You are not allowed to waste more than 2 units of A and 3 units of B. So you cannot waste more than 2 units of A and you cannot waste more than 3 units of B. What are the constraints that you would add to this problem to make sure that you don't waste more than a certain amount? Yes?
100 minus the stuff, the guy over there, must be less than equal to 2.
Okay, 100 minus this?
Minus all this, yes.
That would be amount of waste on raw material 1, I think.
Yes. The other one.
Yeah, you have to use these constraints. Okay, basically, you have to say that, okay, this is the amount of A that you have. Okay. 4x1 plus 6x2 plus 8x3. This is the amount of A that you have. Minus the amount of A that you use. It's 4y. Y is the amount of the final product that you produce, multiplied by 4 is the amount of A that you use. This is the amount of A that you produce. This should be less than equal to 2. So it would make sure that you don't waste more than a certain amount of 2. So more than a certain amount of A. Same constraint would apply to B. You can put there. So you can start playing with these things. So now you can extend our model to one that says maximize the profit subject to these limitation on the waste, for example. Oh, yes. Oh, this part says, what is this number? This number is the amount of A that I produced. What is Y is the amount of final product that I produced. Multiplied by 4, it would give me the amount of A that I used. So the amount of A that I produced minus the amount of A that I used is the amount of A that I produced for nothing. So it's putting a constraint over it. Now, the objective function for this one would be a better or a worse solution than the one without this? Why?
Because you have wasted.
Yeah, because you're adding a constraint. Remember, adding a constraint would never make your answer a better answer. It would always worsen it. And the other way around too. When you add a variable to a problem, your objective function would go up or down if it's a maximizing. Yeah, so when you add a variable to a problem, you cannot do worse than what you were doing before, because you can always put that variable to 0 and nothing would go wrong. So when you add a constraint, your objective would never improve. If you add a variable, your objective would never deteriorate, or whatever you want to call it. Now there is one last question that it's not hard. It's something like what you had in class. So shall I, do you have, okay, before that, any questions about the homework? I think there were some questions about the homework.
You can use the same principle for problem 3B.
Problem 3? Okay, now I have to look at problem 3, really. I don't have the, here, just, yes. Oh, thank you. Aha, good. Yeah, well, you can use the same trick for problem 3B. But remember, problem 3B is in nature not linear. It's talking about the distances in quadratic form. But okay, I have something about problem 3 that I want to tell you, which is a nice idea. So, okay, please, would you listen to me? This is important. Okay. Before going, I'm not going to talk about the solution of 3. It's just some nice idea which is in 3 I want to talk about. Any questions about solving these problems? Somebody asked me questions I forgot just before the class. You're fine with solving them? Okay. Okay, now, if... Yes, you have to minimize the square error. Okay, now, question 3 is asking you to, in part A, is asking you to minimize the sum of distances. In part B is asking you to minimize the maximum distance. Do you have any idea why someone might like to minimize the maximum distance and why someone might like to minimize the sum of distances? Huh? Okay, that's a good question. So let's see what these guys, I will talk about the third one too. So now this has nothing to do with solving. It just has to do with the philosophy behind why somebody might like to do this, why somebody might like to do this. Assume you have a city which is in a square, it's a nice city, and you want to build a hospital there. Okay, very simple question. So you want to make a hospital. You have to put it somewhere. Well, there are different ways to solve. The one way that they analyze such problem is they divide the city into some districts, by some criteria which we really don't care what it is right now. So you divide them into some districts. And then for each of these districts, you define some kind of center of mass, whatever, some center. So instead of worrying about this, you would worry only about these points. So now the question is where to put our hospital. So, and then everything is measured by the distance from these guys. Okay, so you will have some constraints, you would put them there, who cares? Now, one might like to minimize the sum of distances. Okay. This would make sure, let's say that there is no traffic, everything. So distance means time. Okay. So when you minimize the sum of distances, you're going to make sure that in long run, you go as fast as possible to everybody. Sometimes somebody gets sick here. So when you add all the times, you have done it in the shortest time. Okay. There is something. Well, this is a rational. There is nothing wrong with it, but there are some shortfalls. For example, if your city is in a weird shape, you might end up having a case like this. that these are the districts, and this would be your hospital, and there would be one poor guy sitting down there. So basically, if something happens to this, he's going to die. There's no way you can get there. But you have made sure that you are so much near all the population here that you'll be sure. So you should just think of it that if you're going to minimize this, make sure that some pathological case doesn't happen. Now, we can put another criteria here. Instead of minimizing the distance, let's say minimize the maximum distance. Okay. What would this one ensure? This would ensure that thing wouldn't happen, Basically, the maximum one there, you wouldn't be more than a certain amount. You are sure that you can get to everybody in a time span. But then this wouldn't make sure that you're minimizing the whole time, Maybe there was a faster way to go all the places and catch everybody. But so this would be the rationale behind this, which this guy is coming from. Now you might like to do something else. Somebody might say, okay, forget these two. Let's try to minimize the variance of the distances. So what would be the rationale behind this? This is going to say try to give a service level equally to everybody. So we are trying to minimize the difference of the service level. So this might end up giving you a higher thing, but you're going to make sure that everybody gets the same level of service. Now, remember, for all these things, the constraints were the same. I didn't change anything. It was just that what is the meaning of the objective function? So in the third question that you have these things, these are just showing different rationales that you can have, and then based on them you can set up your optimization problem in different ways.
I couldn't understand the third one.
But the third one would, you know what variance is? Variance is a measure of, let's forget variance. Variance is the best one, so let's put it there. Variance is a measure of how your data is scattered. So you're minimizing the scatter, is it ness? Scatterness. Well, my first language is not English, obviously. So you're minimizing the scatterness of your data. You're minimizing. So it's just that this case wouldn't happen in that thing. Hopefully, that somebody would get really fast service, somebody would get a lower service. So you can come up with different measures. You can come up with optimization problems, minimizing this, and putting a limit on these two. So you can add these two in constraints and put one of them as objective. So you would have 3 different cases, putting each of them in the objective function and adding the other 2 in the constraints to make sure that nobody gets a bad service. So it's just, so you would see one problem. Nothing changes. It's the same setting. Different people with different rationale would model it in a different way. That was just some point that I wanted to mention.
All the 3 in one problem. I mean, how do we
you put 2 of them in the constraints. You would say that.
to give a specific value for that?
Yeah, you would say maximum distance is less than 10. You just come up with some measure yourself. Okay. Any other questions? Try to solve the second question by yourself. It's not a hard question. It's much easier than what you did in class. Have a good day. Yes.
Can you find the best fit signal?
Yes.
So like best fit the
Yes, everybody, a lot of you are asking. Remember? It's asking you to find one sigma, not multiple sigmas. So there is one sigma for the whole problem which minimizes the error. Otherwise you can, I think, find a sigma for each of them that your error is 0. Wouldn't make any sense. So you're trying one sigma.
How do you come at y
It's a new variable. Just add a new cell. So it is less than equal to this, less than equal to that. So you just, I cannot draw it here. Just one of the cells, say I'm going to maximize this cell, and then put that cell less than equal to that one and less than equal to the other one. Yes?
Fourth exercise, isn't this wrong? I mean,
you mean the number is a large number?
no, the fourth, because it's a signal.
Okay, what's wrong with it?
I mean,